My name is Ben James. I flew in from Austin, Texas, out in the US, and my role at National Instruments Corporate is the product marketing engineer or product manager for the audio and video test products that National Instruments makes. Now, who has been to Texas before? One person's been to Texas. Who's been to the US? All right, all right. Well, it's a very long trip. I'm still getting over jet lag. But I'm here to talk about digital video to test today. My agenda is I'm going to go over some of the interfaces that we can test. The next thing I'm going to do is go over static image test or protocol analysis, and then I'll also go over audio test. The first one I want to talk about is HDMI. The HDMI interface was introduced in 2003 by the HDMI founders. It's currently held by the HDMI Consortium, and it is for entertainment. It's also kind of grown into the computer space as well, but it supports resolutions up to 1080p 60 Hz 3D. The latest with 1.4B also supports 4K by 2K up to 30 Hz. It also embeds a 7.1 digital audio, so 8 channels of digital audio up to 96 kilohertz, and has some additional functionality in it, such as an embedded Ethernet channel, also an audio return channel. And like I said, it's for in-home entertainment, so Blu-ray players, game consoles, things like that, but it's also started to go into computers. Next up is Mobile High Definition Link, or MHL. Mobile High Definition Link was started by kind of a sister organization or a similar consortium as HDMI. It's called the MHL Consortium. And this is for mobile devices. When I say mobile devices, it's smartphones and tablets. Very similar protocol, very similar specification in that it can support up to 1080p, 60 Hertz, 7.1 surround sound, and it can also charge the phone. The key with MHL is that you take the 2 ports that are on most smartphones today, which is a USB port and an HDMI port, and you combine them into one. So you only have one port. And this way, when you plug in a USB cable, it can act like a USB connection, charge it, connect to your computer and things like that. When you plug in an MHL device, it'll sense the impedance change and switch into MHL mode and start transmitting 1080p 60 Hz video, 7.1 surround sound audio, things like that, as well as charging the phone. And this way you can take your phone and go and plug it into a TV and be able to play a video or a YouTube video off of your mobile device or your tablet. This next one you should all be familiar with because it's the oldest one I'm going to be talking about. It is DVI, Digital Video Interface, and it was introduced way back in 1999 by VISA, the organization VISA. It supports up to 1920 by 1200. It also includes a USB connection in there as well as a VGA connection. You'll see those 5 pins on the right side are actually the pins for the VGA connection. So it includes analog video as well as digital video. This was the standard from VISA that was supposed to replace VGA. VGA being an analog video technology and specification, they wanted to make a digital video technology, a digital video interface to replace VGA. And so while they did that, they made it backwards compatible to VGA. This one was very, very predominant out there until the same organization, VISA, introduced DisplayPort. DisplayPort's by the same organization, so it's the same organization making a new interface to replace the old one. And this one is supposed to be easily be able to interface to DVI, VGA, HDMI. It's going to be the one interface to rule them all, so to speak. Its video resolutions go up to 4K by 2K at 60 Hertz, so it's a very high resolution interface. 7.1 digital audio, same as some of the ones we've talked about before. And it is, again, built to replace DVI, to replace VGA, and to compete with HDMI. So one thing you'll note is all of these interfaces I just spoke about sound very similar. They're all very high resolution. Most of them include the audio signal, and they have some additional functionalities. So they sound like they're very, very similar, but how are they different? The main way that these are different are the applications they're made for, also the way that they are different are the pin count in the actual connector. And the other way that they're different is the auxiliary functions they have. So the applications, I'll run through here. MHL is for mobile devices. HDMI is for consumer entertainment, but again, it's also kind of bled into computer. DVI and DisplayPort were strictly envisioned for computer applications. The pin count varies wildly. DVI having the most pins at 29 pins in that one connector. It's pretty crazy. And MHL is on the other side with only 5 pins. It's the same 5 pins that are in the micro USB connector. So how do those two support similar high resolutions and digital audio and things like that? I'll get to that in just a second. The auxiliary functions can differ from one to another. DVI, for instance, has USB embedded into it. So you have a USB connection inside the DVI cable. Similarly, HDMI also includes an Ethernet, embedded Ethernet inside there. So this is how they're different. Mostly different bodies, different organizations made the different specifications, and how they're supposed to be used is really their biggest difference. But they're all digital video. And the biggest way that they are similar is the communications protocol that they all use to get information from a source to a sink. They all use TMDS, or transition minimized differential signaling. And this is the high-speed serial communication protocol that allows you to get an immense amount of information and data across this cable. 1080p resolution, 60 frames per second, is half a gigabyte of data a second. I'll repeat that. 1080p, 1920 by 1080, at 60 frames per second is half a gigabyte of data a second. So you are moving an immense amount of information every second that you're using a high definition display, right? Well, they all use TMDS, which are twisted pair differential signals. And what's great about this is since they all share TMDS, most of them are passively compatible with each other. So for instance, you can go from DVI to HDMI with a passive adapter, just changing the connectors, just switching the pins and changing the connectors. As opposed to, say for instance, going from VGA to DVI, one's analog, one's digital, you have to have an active adapter. What's nice about that is if they all share the same core communications protocol, you should be able to test them similarly and possibly with the same instruments. This is the 1491. It was released in January, so very recently. This is National Instruments' latest product in audio and video test. And this particular card has got one input for HDMI 1.4. But since we were talking about TMDS, it can also take in DVI and DisplayPort. So as long as you have an adapter, you can passively adapt a DVI or DisplayPort signal and bring it into the 1491 for analysis. And we'll talk through more of that analysis in a minute, but I'm talking about protocol analysis. The other input it's a separate input because MHL is not passively adaptable to HDMI, but it is a similar interface. We also have an MHL input on this. So if you're making mobile devices, here is a MHL protocol analyzer for you. Something else that's very nice to have is a monitor output. So while you're automating this, maybe in R&D or validation or in production, you can also plug it into a TV through this monitor output, and it just repeats it out so you can see what's coming in through the signal. And the last one is that HDMI, that embedded Ethernet channel, the HDMI Ethernet channel, HEC. We also have a hardware breakout of that. So if you have a HDMI device which is using that Ethernet network inside the HDMI cable, you can break it out and test it using this. You can do ping to make sure it's working. You can do stress testing, standard network test through this breakout. Did I skip ahead? I did. So there are many different aspects to the HDMI, DVI, DisplayPort, MHL, many different aspects to those protocols. And with those different components that we need to be able to test, we made different software sets for them. One is the static video analysis. So we have NI-VMS, the National Instruments Video Measurement Suite. And this is for protocol analysis. This is for static video analysis like color bars, if you guys remember those test patterns. Next up is VideoMASTER, the embedded 7.1 surround sound that comes with HDMI. You can test that using VideoMASTER. So we've got predefined tests for different audio test patterns that you're able to test the audio side of things. Next up is the CEC utility, Consumer Electronics Control. This is what allows your Xbox to turn on your TV. So when you turn on your Xbox, you don't necessarily want to turn on your Xbox with a controller and also turn on the TV with a remote. CEC is the part of the standard of an HDMI that allows one HDMI unit to control another. So we have a CEC utility that allows you to watch that traffic. Another one is the EDID utility. Who's worked with EDID before? A few people. EDID is the handshaking that takes place between an HDMI source and sink, say for instance a Blu-ray player and a TV, and when you plug them in and turn them both on, the Blu-ray player will say, "Hey TV," and the TV will say, "Hey, what's going on?" And the Blu-ray player will say, "What resolutions and frame rates can you handle? And what audio do you prefer?" The TV gives its preferences through the EDID table, and then the Blu-ray player starts transmitting according to that table. So this is the handshaking that takes place when the connection first starts. There's been a lot of issues out there with people making set-top boxes, for instance. They will have a set-top box, they'll test it with a few TVs, and then they'll release it into the market and find out later that there's a particular TV out there that's got an EDID table that's giving it trouble. And what you're able to do with the EDID utility is emulate that device. So download that EDID table, put it on the 1491, and make that 1491 act just like the TV so that you can overcome those interoperability issues. And the last one, which I'm not going to focus on in this presentation, I'm actually going to let Eddie from Karma Tech talk about, is picture quality analysis. Does anybody have any problems with picture quality these days? Probably something you don't want to admit, but there are lots of issues out there with picture quality as we're moving into digital because like Fred was saying, when you have digital content, it is very typical that you will take the original content, compress it, send it in some kind of medium, decompress it, and you need to know how the picture quality was affected by that. Picture quality before now was just done visually with human inspection. So you'll have R&D engineers and they'll be looking at a video that's moving at 60 frames a second and they'll say, "Yeah, I think it looks pretty good." And that was what test was for picture quality. Well, engineers didn't like that. They needed a way to test that equipment. They needed an objective score to be able to do that, and that's what picture quality delivers on. And it's all on the same hardware module. So we built a ton of technology into this hardware module. We've also built a lot of software IP, a lot of software that'll help you engineers to be able to develop these HDMI, DisplayPort, DVI, and MHL devices quickly. First, I'm going to talk about VMS, go a little bit more in depth about it. VMS I want to differentiate from picture quality. So VMS is static video analysis. So when I say static video, I'm talking about I'm talking about test patterns. So you see the test patterns up here at the top right, the color bars, the multi-frequency burst, things that had its origins back in analog video, but are still somewhat relevant for digital. So say for instance, when you are transcoding a video, sometimes the color map of the original content to where it's going now gets changed. And so your color bars will show up differently than you expect them to be. And so with Video Measurement Suite, you can make a measurement on that. You can also do things like info frames. Info frames being the non-active region of the frame that include a lot of auxiliary information in there in the HDMI frame. As opposed to picture quality, and picture quality is going to be analyzing dynamic content, so moving things. With VMS, we have a standalone application, we have a LabVIEW API, and we have test and steps. Who is familiar with LabVIEW? All right, I get to pitch LabVIEW. There's a few people who know LabVIEW. LabVIEW is National Instruments' graphical programming environment. When I say graphical programming, Many of you have probably taken a programming class in the past, which is text-based. And you have to be a computer scientist to be an effective user of this text-based programming. National Instruments thought that this was an issue, that it wasn't intuitive enough, that we've got scientists and engineers out there who need to be experts at their domains, their science and what they're engineering, not all be computer scientists as well. And so we made a graphical programming environment 30 years ago, quite a while ago, and it has taken off as the preferred programming environment for engineers and scientists. So the entire idea of LabVIEW is to be able to create a programming environment in which engineers and scientists can develop quickly, have a high level of productivity, and they can remain experts on their field and not be a computer scientist in order to use it. So we have a LabVIEW API. We also have a standalone executable. So if you want to open up VMS as a standalone and start exploring the different aspects of the protocol, you can do that using a standalone application. And then we also have Test Stand. Who is familiar with Test Stand? Not a single hand. Okay, great. I like this because I'll be able to explain these things to you. Test Stand is National Instruments' sequence engine. So in order to automate things, you have to sequence them. And we have a lot of customers out there, engineers and scientists, who need to automate these sequences. And they will spend more time developing the sequencer than they will developing the tests or what they actually want to do. And once they develop it, they have to do sustaining efforts, sustaining development, sustaining maintenance on it. And they end up spending a large amount of their time and budget on building the tool than building the test system that they want to do. So we made Test Stand, which is a sequencing software that allows you to quickly drop down steps, sequence them, generate reports. So once it executes, you'll be able to generate these reports and put it into a database, things like that. So this is the sequencing engine that's out there for National Instruments gear. So we have Test Stand steps. And to back out into Video Measurement Suite, the idea with the Video Measurement Suite is you acquire a video frame, you pick the horizontal line that you want to test, or in the case of InfoFrame, you say that you want to do an InfoFrame test. And you can view the lines to measure here, and then you'll select the measurement that you want to take. You can set limits on it, and video measurement will give you a pass-fail. It's a way of automating a test. So say, for instance, with the color bars, you want to ensure that the color yellow is the correct color of yellow. You'll say it can be between this value and this value, and it'll quickly acquire that frame, look at the color bars, measure what the levels of that yellow is, and give it a pass-fail. And that can bubble up into a result for you to use. Like I was saying earlier, important part to be able to test, maybe not so much in production, but probably in design and validation, is InfoFrames. And so we have a good way to analyze that part of the HDMI protocol, the InfoFrames. It also comes with Video Measurement Suite. Next up is the consumer electronic communication. So this is our standalone utility. We also have a LabVIEW API for it. And this is what allows you to monitor the traffic on the CEC network. So the CEC network that's on HDMI, you're allowed to see what traffic is being sent. Say, for instance, you have a network of a TV, an AV receiver, and a Blu-ray player. That is an HDMI network, and you're able to monitor all the traffic that's taking place on there, as well as send messages in there. Next up, we'll talk about the EDID utility. Earlier, I was speaking about the interoperability problems. They're an issue out there for people developing like HDMI devices. So they'll make a set-top box, and then they'll have this interoperability problem with a TV. Well, why not be able to download all those EDID tables and emulate having all of those TVs? You can do that with the 1491 and the EDID utility. So you're able to explore and edit the EDID tables that are out there, such that you can tell your Blu-ray player, hey, I'm a 1080p TV from Sanyo, or I'm a 720p TV from Sony, things like that. You can change basically the personality of the HDMI device. And last up, I'll talk about audio test. We have a piece of software called VideoMASTER. It's got a test stand step, and with this you're able to do pre-made audio tests on the embedded HDMI audio. So if you've got a single tone playing on all 8 channels, you can go through with VideoMASTER and ensure that the right tone is coming out and it's the right amplitude. You can do auxiliary protocol analysis with the audio. So if you have any need to do audio test on the HDMI, all that comes with VideoMASTER, including audio return channel. So I'll take a second to explain what audio return channel is. This is probably most relevant for people making AV receivers. So this box in the middle that connects between your Blu-ray player and your TV. If you're making an AV receiver, the audio return channel is probably more relevant to you or a TV manufacturer than the set-top box. So this is a typical use of a entertainment system. You've got a set-top box, let's say a Blu-ray player or cable box. It's sending HDMI to the receiver. The receiver is breaking out the audio and powering speakers, and it's sending the video to the TV. So this is a standard use, and something interesting about HDMI is a one-way street. It is it goes from source to sink. It's not a bi-directional network. It's a one-way network. Well, if, for instance, your TV has an antenna on it, the source is actually coming from the TV itself. And you need to be able to get the audio from there back to the AV receiver, because the video starts on the TV and ends on the TV. But the audio has to make it upstream into the AV receiver. And that's what the audio return channel is there for. It is a new component of the HDMI specification that allows audio to go from the TV upstream. So that's something that we can also do with VideoMASTER. But enough talking, let's get to a demonstration. Everyone see this box over here? Anyone curious what it does? This is the National Instruments Multimedia Test Platform. It covers all forms of audio and video that we test, and it is a pretty cool demonstration that I have put together. So the device under test, the product that we're going to be testing, is actually just a little set-top box, an IPTV set-top box. And what we're doing with this is we're streaming content to it over Ethernet. This box is decoding it and outputting it on various audio and video formats. So this little box, you stream content to it over Ethernet, and it's got composite output, component video output, it's got HDMI, it's got analog audio, it's also got optical SPDIF, all of which we just happened to test, so I thought it was the perfect DUT to choose here. And we can walk through the instrumentation that we're going to have to be able to test this. I'll go ahead and launch the demo. It'll run through the sequence one time, but we're basically testing all of these different interfaces on all 4 set-top boxes very, very rapidly. So it's going to fire through and test each of those components for each of the DUTs very, very rapidly. And it does about 400 measurements total, compares those to the limits, and gives everything a pass-fail in about 8 seconds. So it's very high performance, high throughput kind of things. If this is useful, very useful for production applications. You know, you're making these set-top boxes either at board level or end of the line. You need to be able to test all the interfaces very quickly. You plug it in and be able to test each of these in 2 seconds and move it on down the line, either or pass it or fail it. And this way you can avoid having a human look at the screen and say, yeah, I think it's good, or no, I think it's bad. This way you're able to get equipment, test equipment, to be able to say yes or no. So talking about the equipment, let's go through it. Right here we have the National Instruments PXI box. Who has heard of PXI before? We have a totally new crowd here. I love it. PXI is this really revolutionary test platform. It is based on PCI technology, PCI and PCI Express, the same stuff that's in your computer. So it's a very, very high throughput, low latency, great platform, and this box leverages all of that technology, but for instrumentation. So over on the left side, we have a controller. This has a processor, RAM, a hard drive, and this is a very high-end one. This has got this is our new 8135. It's got a Intel Core i7 quad-core processor, It's got an SSD hard drive. This one's got, I think, 10 gigabytes of memory. So this is a very, very high-end controller in here. And then each of these modules is a different instrument. And the nice part about this is if you need to test HDMI and also test analog audio and also test optical SPDIF, depending on your needs, you just get different modules and put it into one test box. And this is opposed to, let's say, for instance, rack and stack. You have the big benchtop instruments. Well, if you want to test all those, you have a box that's bigger than this for each of those. And you put it in a big rack and you have to move it around. All of that fits in one box here. All right, so talking about the instrumentation, we have a board here based on FPGA that connects to optical SPDIF. Optical SPDIF being the digital audio where it moves over fiber optics here. Next up, we've got the new 1491, the one I showed you earlier, released in January. This is for HDMI, MHL, DVI, and DisplayPort analysis. Next, we've got a switch card here, right next to a DSA card, dynamic signal analyzer card. If you've ever worked with an audio precision box, this is similar to that kind of performance, but in a card. And you've got a switch card here to switch through the multiple analog audio. So you don't want to have a ton of these analog audio cards because then you have a very expensive box. Instead, you have one card and a switch to lower the cost of test. And now we have a oscilloscope card, a digitizer card, the 5122. And this is what plugs into this VideoMASTER for the analysis of composite video and component video. So the basic outline of our signal path is we're creating the content on the controller, streaming it over Ethernet to the Ethernet port on each of these set-top boxes here. And then we've got all of the outputs of these set-top boxes connected to our instrumentation for testing. So I'll run it again, and you're able to see the content from one of the boxes coming in. And we're doing all of our analysis on these different interfaces. Say, for instance, composite video, we're going to make sure that the horizontal timing of the signal is correct. It is an analog waveform. You need to make sure that the horizontal timing is working. We're also doing a color bar test. So it's hard to see here, but there's a color bar at the top of the image, and we're making sure that that color bar is represented accurately. It's very similar for component because it's a similar protocol. Also for HDMI, we're doing a color bar test, a blockiness test, making sure the audio of HDMI is working properly. On the analog audio and optical SPDIF, on this particular signal, we have a single tone playing, a kilohertz tone. I'd unmute this and let you hear it, but it's a very annoying tone. And you're able to do a quick analysis to make sure those audio channels are working. So on analog audio and optical SPDIF, we're doing the same tests, and you can see the audio spectrum here. So this is a custom user interface I made. You can do this using LabVIEW, but basically when you've got an inspector, or a technician, or an operator on the production line, you don't want to give them all of the information that comes from each of these devices. You want to simplify it down to just what they need to know. Which components failed, and how did the DUT do overall? And maybe up here we have the different instrumentation, which DUT is it plugged into right now, and how long did it take to test, things like that. So you simplify down what you have on your user interface. You make it very easy for an operator to be able to use this. And you as the engineers can develop this rapidly. This system took me 2 months to put together, but I was brand new. So to LabVIEW and VideoMASTER, or all the audio video stuff. So for 2 months, just a single engineer putting this together was pretty rapid. And I think that's my whole demonstration. I should bring up Fred to talk again. Thank you guys. I appreciate it.